University of Tokyo. Professor Tanaka.
And I appreciate the opportunity for inviting me to Today, I wish to show you the importance of surface compound formation of metal during catalysis. So far, the people explain the catalytic reaction by the concept of absorption. The people explain the surface phenomena as well as catalysis explained by the concept of absorption. That is, molecules in gas phase coming on surface and they make chemical bonds with surface atoms. To minimize the total energy, in some cases the metal atoms on surface move locally. And people call that phenomenon as absorption-induced reconstruction or restructure. Anyway, catalytic process explained by the reaction between the dissociatively absorbed or molecularly absorbed reaction. However, as I will show you, the quite difficult, such simple concept of absorption sometimes very, very difficult to explain the real process taking place on surface. So today I wish to show you an idea based on another concept, that is the formation of surface compound. The idea of surface compound is a little different from the absorption. That is, coming on molecule react with metal atoms which derives from the surface. Some cases from pellets, some cases from steps. This phenomenon is a very, very important advantage of heterogeneous catalysis, because even though the room temperature, we can self-synthesize the functional compound on surface. And such surface compounds sometimes promote the reaction. Sometimes they are the reaction intermediate itself. And some cases, such formed compounds stop the catalytic process. I will show you the practical example to understand the differences between the absorption concept and the formation of surface compound. Good example is hydrogen absorption on nickel 1,1,O surface. Perhaps you are not so familiar about the 1,1,O surface. This is the model of 1,1,O surface. When hydrogen is absorbed on this surface at temperatures lower than 220 Kelvin, we can observe the 1/2 structure. About this leaf pattern structure, the Professor Arthur Group precisely studied and published such model, here low model. However, the room temperature absorption on same surface, we can observe the 3 1/2 leaf pattern. And this structure is reversible. Low temperature structure is reversible. That is, by removing hydrogen, the surface back to the 1/1 structure. However, room temperature, this is irreversible. So it's quite difficult to understand what kind of difference exists between low temperature and room temperature. And quite recently, we can understand clearly. That is, the last year, Professor Bezenbacher and his group published very, very beautiful SPM image. They show the green surface of nickel 1,1,O and expose this surface to hydrogen. They observe the formation of surface compound, one-dimensional surface compound, as you can see here. That is quite different from the concept of absorption. That is, the former case is typical example, low temperature phenomena is the typical example of this absorption-induced reconstruction. However, the second case is the formation of surface compounds. So that we have to be careful to explain or consider the catalytic process. The temperature is not so low. I will show you one good example, interesting example, which we did before. This is the hydrogen-deuterium exchange reaction. This reaction, this is the case when this H2D2, 12-tol H2D2 mixture contains a small amount of oxygen. This case, only 10 to the minus 4-tol oxygen contained in 12-tol hydrogen. As you can see here, HD formation perfectly starts in certain period. And here shows the in-situ lead pattern change. Here shows the in-situ lead pattern change. And here shows the gas phase oxygen partial pressure. Gas phase oxygen partial pressure degree with reaction time. And completely remove the gas phase oxygen, suddenly started the H2D2 equilibration reaction. And during this period, we observed a very strange pattern of lead pattern, hexagonal lead pattern. And in-situ high resolution yields indicate the formation of hydroxide overlay. So, this period, hydroxide overlay covers the surface. So in this case, we can say the surface is covered by hydroxide overlay, which is the intermediate for water formation reaction. However, that stops the H2D2 equilibration reaction perfectly. That is this case. Another interesting phenomenon of the formation of surface compound might be the structure-intensive catalysis. I wish to show you the two interesting examples. One is the methane formation of liquid. The other is the ethylene oxide formation reaction of silicon. This is very famous experimental result given by Professor Goodman and Professor Campbell. Anyway, such typical heterogeneous catalytic reaction is insensitive to surface structure. Why this interesting reaction is structure insensitive? That is the interesting question for me. And as I presented in poster at Budapest Symposium, in the case of methane formation reaction, the surface is covered with same structure surface carbide. That is, surface carbide is the reaction intermediate for this reaction. And the same surface carbide covers on nickel 100 and nickel 11 surface. That is the reason of the structure insensitivity. And chemical unit, not the structure unit, but chemical unit we can describe by such model. Quite fortunately, Professor December has sent me unpublished, very interesting new data. He succeeded to catch the carbide, SPN carbide. As you can see here, 4 nickel atoms. He speculated carbon might be this here. That is, just indicates the formation of surface carbide as taking such chemical units. That is the reason of structure intensity. In the case, if such surface is close to hydrogen, of course, hydrogenation occurs. And we can detect by using high-resolution yields, CHX or CTX formation on the surface. This result was presented in poster in Budapest Symposium. Anyway. The formation of the ethylene oxide is a little different from the former case. That is, as Prof. Campbell described in his paper, the surface during catalysis, only the adsorbed species is oxygen when to the catalyst back to the ultra-high vacuum chamber. And he believes surface is covered with partly by oxygen, adsorbed oxygen. But that is wrong, might be, because in the case of silver, when silver surface is exposed to oxygen, surface is covered by new compound of silver oxygen malt, one-dimensional compound. As I published in this paper, here shows one-dimensional surface compound, silver oxygen linear compound, making self-organization by making the primitive N-by-1 structure. And this case, catalytic reaction taking place on over the surface compound. So the starting structure is not so important in this case. That might be the reason. And finally, I wish to show you our recent result, that is the platinum body. That is very interesting catalyst. But nobody clearly understands why this is so efficiently works. As I told you, the formation of surface compound and dynamic properties of that is very important for this catalyst. But some people know platinum rhodium surface has a very unique distribution. That is, topmost layer. This is given by the process Song by using atom flow confinement method, layer by layer analysis. The one first layer, topmost layer is platinum rich. This is the case of clean surface. But the second layer is platinum depression. That is rhodium metal rich surface layer. And deeper than third, almost the bulk composition. And when oxygen comes on this surface, I will show you the displacement occurs. Because oxygen prefers to make bond with rhodium. So the displacement between topmost layer and second layer rhodium occurs during catalysis. I will show you the example. This result was published here. The crystal is heated up. Platinum rhodium 100 alloy surface, thin crystal surface, heated up step by step in oxygen, 10 to the minus 7 total oxygen. We can observe that such very unique surface link pattern, 3 by 1. And OJ intensity change is indicated here. This yellow color spot, that indicates the ratio of platinum and rhodium. That is, these degrees indicate the increase of surface rhodium. And this is the oxygen-rhodium ratio. So the increase of solid sample indicates the increase of oxygen. This temperature range, the formation indicates the formation of rhodium oxygen surface compound. And the same surface compound formation we observed during the reaction of NO and hydrogen. Here shows that this is in-situ lead pattern change, and here shows in-situ OJ intensity change. When surface is exposed to NO, we observed immediately after center 2 by 2 but few minutes after started the formation of 3x1 structure, and finally surface is covered with 3x1 pattern. That is exactly the same structure as the observing object. And however, if this surface is exposed to hydrogen, the oxygen very quickly removes, even though the temperature -8 tall hydrogen. And this pattern immediately disappears, and center 2x2, this pattern appears. And the nitrogen increases. So this is the nitrogen overlay. This is oxygen rhodium surface compound overlay. I have no time to talk about this one. Only focus on this topic today. That is, we can summarize the such model. The platinum rhodium alloy surface, it is three surface topmost layer platinum, second layer is rhodium, deeper than third layer is alloy, by bulk structure. And exposed to NO oxygen, we can prepare the topmost layer rhodium, but the rhodium makes the rhodium oxygen surface compound. And that is the first reactive, so the reaction with the hydrogen back to the original surface, also heating up the original surface. If such speculated model is correct, we wish to know what is the minimum requirement for this effective, efficient catalyst. Perhaps 3 atomic layers sufficient. That is rhodium and 2 platinum layers. To demonstrate that, we intend to make the limit model of this efficient catalyst by using electrochemical deposition of rhodium. On platinum surface, we try to deposit the rhodium. I have no time to show you the instrumental development. Anyway, the result was shown here. Here shows the twin surface 5x20 structure, and this surface is bottom shown here. And on that, we deposit rhodium. The bottom graph changes quite drastically. And this surface, SPS shown here, a small amount of rhodium deposition. Expanded spectrum shows here. And this pattern change is like that. Green surface changes one by one, and diffuse background becomes little diffuse. And this surface is exposed to NO or oxygen, just I expected, 3x1 surface of rhodium oxygen overlayer making 3x1 structure with acid to prepare. And that is heated up again back to the site structure. So we can conclude the minimum requirement is the 2 platinum layer and probably 30% or something rhodium. That is the effective catalyst. Limit model of the effective catalyst. That is my conclusion. And why the such surface compound is so reactive and so active, that might be we can describe by this cartoon. Thank you for your attention.
Thank you very much. Any questions? Please identify yourself.
Lanny Schmidt from the University of Minnesota. In the platinum rhodium alloy, low temperature heating in oxygen will make bulk rhodium oxide. And then that will come up to the surface and form a thick layer of oxide, of a rhodium oxide phase. And when that is reduced, you'll have a definitely enriched rhodium surface.
What is the temperature?
Oh, well, low means, that's the question, isn't it? I mean, you must be low enough that the bulk rhodium oxide will form in an oxygen atmosphere. So I'm asking, are you in a situation where you're above bulk oxide formation? Because I think you can get quite different results if you're just calcining at low temperatures when you get a rhodium oxide precursor before you reduce in hydrogen.
Yes, your question might be lower than this temperature.
I suppose so, yes. I mean, you only have 10 to the minus 7 torr of oxygen.
Yes, that's right.
And so you don't make the oxide.
That's right.
That's
That is the reason. And low temperature might be controlled, the formation is controlled, the diffusion rate, replacement rate of the platinum rhodium. Low temperature is not so high. That's the reason. But when the surface is enriched by rhodium, lower than this temperature, we can build a free-valence fraction.
Did you identify the silver-oxygen compound on the silk surface? You said there was oxygen-silver compounds being found during the oxidation reaction.
There is no, that is only the oxygen exposure process, not the during the ethylene oxide formation process. Ethylene oxide started during the catalysis process. Campbell emphasized only to observe the 2 by 1 structure, but the exposed to oxygen, we can observe N by 1, depends on the calories.
Okay, so that's just at some oxygen in the growers.
Yeah, they're making the one-dimensional silver oxygen chain.
Yes.
And that is making N by 1 odors. And the quite interesting point is the copper also the same, but the copper chain has a stronger attractive force than silver. So always make a 2 by 1.
And did you expose such surfaces to ethylene?
No, still not.
Please.
I think I still don't understand what is the crucial difference between the, for example, oxygen-covered surface and the surface compound of metal and is the regularity of the arrangement is a crucial difference between
To that question, this is not my data, but you can quite clearly understand. This is the ABC is the changing exposure time. What kind of changing occurs? This is the 1,1,O surface hydrogen given by Professor Weizenbach. You know, here the nickel atom moving out, growing the trap, and newly formed such new compound. That is not the absorption, but the formation of some compound. That is
Ultimately is repeated for the definition of surface compound.
not the definition, but the practical phenomena. Not the program of definition, but the...
At the actual reaction condition at high temperature, it's not easy to differentiate between the surface compound and the oxygen or ethylene covered surface. Probably the surface changes very dynamically at high temperature under the actual reaction condition. And then once the surface the concept of surface compound.
Yeah, as you like. Depends on you.
May I ask a question? It is the question of the concept of order and whether it is retained at the catalytic temperature. You clearly show good examples of order, which you call a surface compound. That is a reasonable thing to do for the lower temperature conditions. But the key question is, how much of that order is retained when you raise the temperature by, say, 200 Kelvin?
That is very, very important question. During catalysis, such surface compound dynamically the formation and goes on to the product. That is dynamically balanced on the surface. So in some cases that we cannot get an ordered state. Typical example is the carbide formation. We build carbide completely cover the surface even inside. That is the same as single crystal. To identify the intermediate, if we can get the single crystal of intermediate, we can get the structure. However, during the reaction, of course, intermediate doesn't make a single crystal. That is the same on surface. Intermediate probably dynamically forming and disappear such kind of balance dynamically. But if accumulates, that makes up organic element.
Thank you.